This is the fuel cell testing rig. Here is our fuel cell testing system. So today we will test a solid oxide fuel cell, but in a solid oxide fuel cell we will see how to fabricate it and how to make it and then how to test it. And we will test with different way. In IV curves, fuel cell performance, then is polarizations curve, like what kind of losses inside the cell, like ohmic losses, activation losses and some other losses. So let's start from this. We'll see here are we have synthesized before is a nanocomposite powder is anode, here is electrolyte and here is cathode. These are three layers for one single cell. So we will start from anode layer. We will put about 0.3 gram inside this dye and then just few press to make it homogeneous layer. After that we will use about 0.25 gram electrolyte and then again just press it to make it more clear, and then after that we will use a cathode powder is also about 0.25 gram, and then again we will is like this. So now we will press it with this one is called cold press, and a cell can be fabricated with two different pressing. One is hot pressing and other is cold pressing, but this is we are using here is a cold press for simple fabrication process to test in a laboratory. So we will use here pressure about 200 kilogram per centimeter square. Here then we will release this pressure. We will take out this one and we will press it again to take out the cell. This is the very simple way how to fabricate the single cell. So this side is anode and other side is cathode, and inside in the middle is electrolyte layer. This is the silver paste. Silver paste always can be used to collect the current. So in this single cell we can paste a silver on one side to collect the current. This is the important because we need to check its performance. So it's now such kind of white layer is on the surface of the cathode, and on other side we are using nickel as a current collector. So on both sides there should be some kind of current collector. So we will put this cell inside the holder and just press it, and this is here are two springs is very flexible. Just to hold the cell just press little bit and then just screw this holder, and you can see this cell is air inside and is in the side the holder, and we will use here this is flow channel for the fuel gas and this is for air. So we will put this one. This is the furnace, and this furnace is a high temperature furnace. It can operate till 700 centigrade. So but we will use from 300 to 550 temperature. So we will put like this. This is the just for holding the cell. So here is a hydrogen cylinder. So we will use this hydrogen as a fuel in this cell, and this is the flow for the hydrogen on anode side, because this side is for anode side for the cell, and in between this is the these two channels is for cathode side, because cell is on two surfaces, one surface is anode and other surface is cathode. So on cathode side we are using this air, and we can control air from this side, and we can control hydrogen from these flow meters. So we are using hydrogen here about 100 milliliter per minute. This is the instrument is a Japanese instrument. It can be used for fuel cell testing for different characterization. For example, it's IV curves and some other impedance, and some more for different polarizations curve, and even for cyclic voltammetry we can use this one. So but now we will use for fuel cell IV curves. So here we put positive and negative terminals on anode and cathode sides, and we will see how fuel cell work and how can we get its voltage and current. So let's see on the computer screen. Here is a on y-axis there is a voltage, on x-axis is the current, and also here is the current on red you can see, and here green is a voltage, and here is the time if we want to see is the stability of the cell. So this green line showing the voltage of the cell, and red line showing the current of the cell. So this is the IV curves for the fuel cell, but we can this simulate on the different program in Origin on the computer, and we can show you later the exact IV curve and what is the exact performance of this cell. So now let's see, this is the impedance. So this impedance curve we can get from the cell is basically is the polarization and resistance of the cell. So we can see from this is less than 800 milliohms. There is the resistance. This is the real resistance, and there is the imaginary resistance, and we can see this is the curve for that cell, and this curve basically shows the ionic part of the cell. And here are the different with respect to frequency, we are applying different frequency from 1 to 100 kilohertz, even we can go for megahertz. And here is the between the imaginary and real part, and here is the between the phase angle of the cell and the frequency. So these are the some parameters we can adjust in different way of what we need. We have shown you some small single cells, but is for using as academic purpose. This is the scaling up cells. So here is 5 cross 5. This is the this is the size of these cells. 5 cross 5 is and its area is 25 centimeter square. You can see inside the electrolyte white layer, and one is this side is anode and other side is cathode. This is the 3 layers single cell, and we can get from this cell is about 10 watt power. And here is different designing. This is the some more scale up cell. This is the 10 by 10 cell, and is same structure like before, is anode, electrolyte and cathode. Here are the some flow channels for different gases. So how we test for this? We have a different dies to test this one. Inside you can see there is some flow channels for the hydrogen and oxygens. So we can put that cell here inside and here, and then we can adjust like this, and we can test in the furnace at 500 temperatures. So here are some small films, very thin you can see there are small film. This is anode layer, and also downside is electrolytes and cathode. This can be fabricated with hot pressing, but before we have done with cold pressing. How to make a stack? So I just want to show, here is our small stack system. So this is the bipolar plates, and we can put, this one is here, and then is sealing, and then again there is the interconnectors here, and then we can come and other cell. This is the second cell, and if we want to make stack for 5 cells, then we can put in this way, step by step, and we can adjust like this. This is also a bipolar plates. So this is like this 2 cell stack, but here is one ready for 5 cell. It's already, we can get 50 watt from this stack system. One cell is for 10 watt and 5 cells is 50 watts. So 5 cross 10. So this is the one design of the stack system. But we have some different designing. This is some specially for gases, and for liquid fuels, you can see this is some special design for liquid fuels. It can operate with ethanol and methanol, and this is a 3 cell stack. And we can get about 150 watt from this cell. And this is the complete with sealing, with everything, is a complete cell. We can say like a fuel cell product for different application, especially for APUs.